for the last topic of this week. What happens when the characteristic equation of a second order linear homogeneous constant coefficient ODE has complex roots? Let's go for it. The ODE we're looking at is a y second plus b y prime plus c equals to 0. We associate to that a characteristic equation, a r second plus b r plus c equals to 0. And this characteristic equation has complex roots. It happens when b squared minus 4ac is smaller than 0. And then we have as roots lambda plus the imaginary number times mu and lambda minus the imaginary number times mu, where we assume when we're taking lambda and mu real and we write the imaginary number as I. Side note, R1 and R2 are complex conjugate. The sign in front of the imaginary part has flipped. We would still like to write that y1 is the exponential of r1t and y2 is the exponential of r2t, but what does that really mean? So we now have the exponential of a complex value, because r1 is complex. Well, we can write it out and notice that e lambda t is multiplied by the exponential of I mu t. So we simplify the problem from having the exponential of a complex number to what is the exponential of an imaginary number. What is the exponential of I mu t? Well, let's first look at the Taylor series of the exponential. So just the exponential of t, we take the Taylor series at 0. Then we have a structure that is very nice. Exponential of time of t is equal to 1 plus t squared divided by 2 plus t to the third divided by 3 factorial plus infinitely many terms, all in the form tn divided by n factorial. So the exponential is equal to the infinite sum for n going from 0 to infinity of t at the power n divided by n factorial. And this is true for any real value of t. Let's just assume it's also valid for imaginary values of time. So we're taking the exponential of the imaginary number times time, and we say that it should follow the same rule as the exponential of the real value of time. So we now have a sum going from n equal to 0 to infinity of imaginary number times time, all at the power n, divided by n factorial. And obviously we can distribute the power, so we have a sum from n going from 0 to infinity of I at the power n, t at the power n, divided by n factorial. Then we remember the structure of the powers of the imaginary number. We have that the imaginary number at power 2 is equal to minus 1. Then, if we take in the next power, imaginary number at power 3 is the imaginary number times 2 times I, so it's minus I. In general, the imaginary number at a even power, so at the power 2k, is equal to minus 1 at the power k, while the imaginary number at an odd power, so at the power 2k plus 1, is equal to minus 1 at power k multiplied by I. So we can use that to split our infinite sum that we use to construct the exponential of an imaginary time. We can split it between even and odd indices. So we first have a sum from 0 to infinity of k with the even indices. So we have t at the power of 2k and the imaginary number at the power of 2k, that is equal to minus 1 at the power k. All of this divided by 2k factorial. Plus the imaginary number multiplied by the odd indices. So it's the sum from k going from 0 to infinity of t at the power 2k plus 1, I at the power 2k plus 1, that we simplify by writing minus 1 at the power k. The imaginary number is already in front of the sum. All of this divided by 2k plus 1 factorial. And you might recognize it, otherwise I encourage you to try it out and compute it for a little bit, that the first block is the cosine of t, and the second block is the sine of t, with an imaginary number in front. So the exponential of it is equal to cos t plus I sin t. This is called the Euler's formula. It allows us to switch between exponential of something imaginary down to cosine and sine with a real part and an imaginary part. What it means is that when you're taking the exponential of something purely imaginary, you're actually computing a rotation, something that oscillates over time. The exponential of something real is something that tends to infinity very fast, or 0. This is the usual exponential curve. But the exponential of something imaginary is oscillatory between plus 1 and minus 1. So it then follows that the exponential of minus the imaginary number times time is cosine of t minus imaginary number times sine of t. And in general, the exponential of lambda plus or minus I mu times t is equal to exponential of lambda t times cosine of mu t plus or minus imaginary number times sine of mu t. So we can now that we have this understanding, we can go back to our solution of the characteristic equation and use it to construct new solutions. Let's check that for r complex, the derivative with respect to time of exponential of rt is equal to r times the exponential of rt. This is the thing we use in order to take advantage of the characteristic equation. So if this fails, the use of the characteristic equation fails as well. So this is kind of important to do this check. And it's a bit cumbersome, but you write it all out. We use that r is equal to lambda plus I mu, and we retrieve exponential of lambda t times cos mu t plus I sin mu t. We take the derivative with respect to time of the first block and the second block. So it's the derivative of a product, so it is the sum of the derivative of each part. So we have lambda e lambda t multiplied by the same block cos mu t plus I sin mu t plus e lambda t times the derivative of the parenthesis, that is mu multiplied by minus sine mu t plus I cos mu t. And if you check things out, this is indeed lambda plus I mu t multiplied by ERT. That is the same thing as before. So our check succeeds. We can take the derivative of a complex exponential and have the complex term in front times the same complex exponential. So we can use a characteristic equation. What is the Wronskian when we're talking about complex roots? So we're talking about y1 and y2 that are exponential of r1 and r2 respectively multiplied by time, that are exponential of lambda t multiplied by cosine of mu t plus or minus, depending if you're talking about y1 or y2, imaginary number times sine mu t. We can choose as fundamental set of solutions the real part of y1 and the imaginary part of y1. So we choose u equals exponential of lambda t cos mu t and v as exponential of lambda t sine of mu t. And we compute the Wronskian in this case. The Wronskian becomes mu times exponential of 2 lambda t. And it is non-zero for every choice of time if mu is different than 0. But mu is different than 0 because otherwise we wouldn't have complex values. So the Wronskian is different than 0 all the time. As a conclusion, if you're looking at solutions for second-order linear homogeneous ODEs, then when the characteristic equation has a complex roots, the solutions are in the form C1 exponential of lambda t cos mu t plus C2 exponential of lambda t sine mu t. Let's look at an example. Y second plus y prime plus 1 equal to 0, with y at 0 is equal to 1 and y prime at 0 equals to 2. Then we build a characteristic equation. The characteristic equation becomes r squared plus r plus 1 equal to 0. Then we have the solutions that are r is equal to minus 1 plus or minus square root of 1 minus 4 divided by 2. That is minus 1/2 plus or minus imaginary number times square root of 3 divided by 2. So we have a complex exponent of our exponential. So our solution is in the form C1 exponential of the real part of r, so exponential of minus 1/2 t, cosine of the imaginary part, cosine of square root of 3 divided by 2 multiplied by t, plus C2 exponential of the real part, so exponential of minus 1/2 t, sine of the imaginary part, so sine of square root of 3 divided by 2 times time. We use the initial conditions in order to fix C1 and C2. So because sine at 0 is equal to 0, the second block disappears when computing at 0, so we have C1 is equal to 1. And then we have to compute y prime in order to compute C2. And y prime is a bit cumbersome, but when we compute y prime at 0, all the terms involving sine disappear and all the exponentials of 0 become just 1. So we have y prime at 0 is equal to minus 1/2 C1 plus square root of 3 halves C2. And we can solve for C2 and it's 5 divided square root of 3. So now we have the full solution. Y is equal exponential of minus 1/2 t cosine of square root of 3 divided by 2 time plus 5 divided square root of 3 exponential of minus 1/2 t sine of square root of 3 divided by 2t. Let's look at this solution a little bit because it has a structure that we will see many times when looking at this type of equations. We have the exponential of a negative number, so it states that everything is decreasing over time. And we have a sine and cosine that are oscillating over time, by the way, with the same frequency. So as a general statement, when we have complex roots, we have a product between something that is oscillating, sines and cosines, and an exponential. An exponential that might have a positive or a negative exponent, but that is what tells us about the long-term behavior. Oscillations appear with the complex root, and the exponential states if it has a decay or a growth.